All right, hello. We're in the lead up to our AP exam. Let's go ahead and discuss some topics. Just a few details to get down. First one is, and I want you to write this one down, sequential search or linear search. They mean the same thing. Linear relating to having all data in a line. Sequential relating to all data lined up in a sequence, both meaning the same thing. So take a look at this list of numbers. Here are the indexes for those numbers at the top here, and then at the second row we have the numbers themselves. A linear search or a sequential search is where we're looking for a value in that list, and we're going to just go we'll talk about that. You see, the thing I want to say first about it is this is a very easy algorithm. It's very, very simple, not only to understand, but even to write. Now, this then gives us a good way to jump into the definition of brute force. Think about the term brute force. Think about the last time you forgot a password and then just kept trying various passwords that you remember from your head until you got the right one. Maybe you got locked out of your phone and you have one of those little patterns and you just keep trying patterns until you get it right. Maybe it's just a 3-digit number and you just had to keep guessing numbers. All of those things are examples of brute forcing algorithms. Brute force is where we take a very obvious and simple solution to the problem. And in the case of a search, the easiest way to search for a number is to start with the left value, check if it's the one we're looking for, then check the next one, and so on and so forth until we find the right value. In the case of our example here on the left side, you can see we're looking for the number 33, and we just check every number till we get there, and when we do, we say, cool, we're all done. I've also converted it into a slightly less efficient version over here. Remember that this isn't Python, it isn't JavaScript, it isn't anything else. This is the pseudocode that we see on the exam itself and our exam practices and Albert and all that. You start off with a target, as in a number you're looking for, and a list of values. And then I also use this thing called found. I just have a variable called found that equals false. And we're going to pause on that one. Come back to that one a little while later. And then for each element in that list, let me switch over to for each element in that list, we check and see if that element is equal to our target. If it is, we say, hey, we found it. Change that found variable to true. And then after we're done searching the whole list, I see if that found variable was false. If it was false, then I say, oh, hey, we didn't find the number. If we never found 33, then at the end of it all, we do want to let the user know that. But if we did, we can just let them know immediately. This algorithm is divided then into 3 parts. Just draw these lines right there. The 3 parts being saying up the variables, searching through it to see if we find it, and then handling what happens if we didn't. Alright, so that's linear search, very simple. Different than that is binary search, and I just listen very carefully to how this works. The first thing to know about binary search is that it requires a sorted algorithm. And it needs to be sorted because it's going to take advantage of that sortedness about it. So take this example here. Let's say I'm looking for the number, well, they're using 4, but I'm going to use the number 3. So let's say I'm looking for the number 3 in this thing over here. So I'm going to write the 3 up here. So if I'm looking for 3, what binary search does is it starts in the center, the very middle element. Now, what is the relationship between 3 and 7? Well, obviously 3 is less than 7. So here's the question. If this list is sorted and the number we're looking for is smaller than the middle element, is it at all possible that our target is going to be over here on the right side? No, of course not. So I can actually just ignore those 4 numbers. And actually I won't cross them out just because we're not actually erasing data, but you know that we don't have to check those numbers over there. So then I check the middle element between that 1, 7, and 1. That's going to be our 4 here. The relationship between 3 and 4 is 3 is less than it, so I know that it can't be to the right. So again, I skip these two and I check the middle element here, and that's when I find my 3. To put that into an animation, you can see us doing it right here. We search the middle element and just keep checking the middle and moving the cursor around until we get to the right place. So in this case of this binary search, we're looking for 37. We start at the middle. 37 is bigger, so we go to the middle on the right. 37 is smaller, so we do middle on the left. And then we go here. Notice how we just did 3 comparisons as opposed to sequential search, which had to check all of them. Now in this case, the differences is going to be pretty minor. You know, computers can check 11 numbers pretty rapidly. However, imagine that instead we had like 1,000,000 numbers. You know, imagine that this just goes on and on and on, and sequential and the 37 was like way over here. It would take forever to get there, except for the binary search, which cuts it down logarithmically. When I say that it cuts it down logarithmically, I mean that as in binary search is named because it cuts runtime not in half, but rather down to being the logarithm base 2 of the number of elements. Now you don't have to worry too much about that, but just understand that because binary search keeps ignoring numbers, keeps skipping around, it goes much, much faster than sequential search. Binary search requires, however, a sorted list, like this one, requires them all to be in order. There can't be any out of order, or otherwise that could throw the whole thing off. And it does need a lot of elements. These two, this isn't really like the best example right here with these two, just because the difference will be so minimal. But again, binary search is much more efficient than sequential or linear search when we have a gigantic list. You know, think a couple of hundred, maybe even 100,000 or 1,000,000 elements, which in today's modern world is not all that unlikely. There are a lot of really large databases out there. So that kind of leads us into efficiency. Now, there are 3 terms I want you to know, but we'll come back to that. There are really two concerns for efficiency in this class. I should say that over here in this class. And those two are the number of steps and the amount of data produced. This one, because of the storage space of it, you know, if we have to store massive amounts of data, that's going to be costly. You know, you guys have seen your hard drives in your computers, and maybe it has 500 gigabytes of space, and you know that all the files you have in your computer, they take up space, and you can run out of space. So the storage is a concern. But usually the most one you'll see us talk about, or the one to see us talk about the most, is the number of steps. And that is in number of steps. Why did I write it twice? Well, why write that twice? Because I want you to see something. Number of steps is not seconds. We don't measure time in time. We measure time, or run time, in the number of steps. Yeah, so your science teacher is going to hate me for saying that. But we don't use seconds, minutes, hours for determining runtime. We use the number of steps. The reason is because the amount of time, the actual like literal time, as in seconds, varies wildly among different computers. The number of programs that are running, the temperature of the computer, the age of the computer, you know, just all kinds of factors affect how long a program will actually take in seconds. So a programmer can't really use anything with that do a lot with that information. Now, before anyone corrects me, yes, indeed, benchmarking is a thing, and that is another discipline that does indeed use seconds to determine how efficient stuff is. We won't be worrying about that for this class. For this class, just worry about the number of steps, because that's the main thing a programmer can use to determine how efficient they are doing something. So by knowing the number of steps, we are able to figure out how efficient an algorithm actually is. If we look at it and we say, okay, like back to sequential and binary search, sequential search, the more elements we have in that list, the more steps we have to do. We would say for linear search or sequential search, we say that it takes n steps, because it's n number of comparisons, because that's every time you're checking for the value. It takes n steps, where n is the number of elements in the list. Meanwhile, binary search, the binary search takes what we call log n steps, which if you haven't taken that math class yet, all that means is that binary search takes less time. And whereas each time we add another element to the linear searches list, it's going to take one more step. For binary, it might take a good 2, 4, 8, 16 new elements in order to make binary search take an extra step. You could have a 12 elements list that might only take 3 steps, and then add in 3 more elements, and it still only take 3 steps. Binary search is very nice like that. It's less reactive, we might say. In short, efficiency is affected by the number of steps, because that's how we can determine how to make an algorithm more efficient. If you made a program and it used a linear search on a really big list, well, you probably want to notice that, so that way you can change over to the binary, as long as your data was sorted. So then the 3 words I want you to have for efficiency are these: undecidable, unreasonable, and unsolvable. Undecidable means that the algorithm does not work for all inputs. If we're talking about an undecidable algorithm, that means that it works for certain cases. Like I can take this algorithm and try it on a problem, but it won't always work. And it has very special cases. We did, again, just talk about binary search. That is, in many ways, an undecidable algorithm. It only works for certain kinds of input. Now, we don't usually call binary search undecidable, just because we usually just say binary search requires sorted lists. We have a very clear pattern for it. Undecidable is really for when we can't predict whether or not something will work. There's no clear pattern for what types of input works and what kinds of input doesn't. When we talk about a problem being undecidable, it means that we need different algorithms for different parts of it. Not just to solve little pieces of it, but rather to solve different inputs for it. Undecidable means the algorithm does not work for all inputs. Unreasonable, meaning the algorithm takes too long to work. And again, too long, we aren't measuring time in seconds, we're measuring time in steps. If it's unreasonable, the algorithm takes way too many steps to actually work. And that can be really bothersome. It could be something like, oh, in order to search this database, you'll have to wait 3 years. And that's just preposterous. That's unreasonable. So unreasonable is where the algorithm takes too long. Lastly, unsolvable. The problem is not actually solvable. Now, when we have an unsolvable problem, we'll talk in a moment what we do. It's something called a heuristic. But just in general, unsolvable, very self-explanatory. Okay, a heuristic algorithm. And I know in class I was saying heuristic a lot. It's because I saw the EU when I thought it was German. But we're going to say heuristic. So, some problems are unsolvable. Hey, we just learned that word. Or they're taking an unreasonable amount of time. Guys, be very clear that those are the 2 conditions for why we would use a heuristic algorithm. So when they do, And there are some examples. You may have heard of some of these. Traveling salesman, the exact value of pi. This one you've definitely heard of. Or P versus NP, which we're just not going to go into. For these problems, we can use a heuristic. Now, a heuristic algorithm gets a close enough answer. Let's go ahead and think about it. We'll get to that. Let's talk about pi for a moment. So pi is 3.14159. ... Yeah, it's a lot of things, isn't it? Pi is a really, really long number. And I use pi because it's a perfect example of a heuristic algorithm. You see, we have when you're in your geometry class, this is probably good enough, right? You know, we know pi goes on forever. Like, we literally cannot get an exact answer for pi because it goes on forever. Someone in class today pointed out a website which had it to 1 trillion digits. You know, that's insane. You know, it goes on forever. However, for a problem that doesn't really require that much exactness, 3.14159 is good enough. And that's the real test for a heuristic algorithm. When a problem is unsolvable or would take way too long to solve, you know, maybe even years to solve, we say we decide to use a heuristic algorithm instead in order to give an answer that's close enough, you know? So in the case of pi, these two are not equal to each other, but they're close to equal. You know, they're close enough for whatever purpose we're using. So for what solutions for whatever solutions we can say are close enough, that we can use a heuristic algorithm, where it will either just not solve it all the way, you know, it will solve most of the problem, get to a close enough point and say, okay, to go on any further, it would take years to finish solving this problem for a computer, so we're just going to stop it there. Or if we get to a value where we're like, okay, we literally can't get an exact value, this is close enough. So those are the two times where we use a heuristic. And let's address something next. So there's this one question on Albert. It asks, which of the following statements about runtime are true? And one of them, the very first one, was there is always a way to solve a problem in a reasonable amount of time. And this part I want to focus on. So a heuristic algorithm, we say, is a way of solving an unsolvable problem. But the thing is, we don't actually consider that to be true because heuristics don't actually solve it. They get a close enough answer, but it's not really a real solution. In many cases, good enough isn't actually good enough. You know, if we're sending people up to the moon, you know, or even, I mean, we sent people to the moon. We're now aiming towards Mars. You know, if we're sending someone to Mars, we really can't mess that up. Good enough might take on a different definition, and we need a better solution. When we lack an exact answer to a question, usually we don't consider it answered, and we keep trying to solve it closer and closer. We assume that there will always be some problem that we can't solve. You know, that's just a basic idea in science, that there's always going to be a problem that we are trying to solve. We will never actually find, we will never actually have it where we solved all the problems. In addition, we assume that there are going to be problems which will never ever be solved. So we say there is not always a way to solve a problem. And because that word solve, we say, even when we have a heuristic algorithm, we don't really solve the problem. It's still considered unsolvable. That's it. All right. Hope that helped. See you next time.